Hello, this is my entry for the 2023 Summer of Maths exhibition, and it covers the equations seen in the thumbnail. This video is essentially all number theory, but with a tiny, and I do mean tiny, amount of calculus. But fear not, because there's no power series discussing integrals or repeatedly banging your head into your textbook where we're going. Its main subject is the arithmetic derivative, which, roughly speaking, applies the product rule from calculus to the natural numbers. Now that may sound overly complicated, but my hope is that by the end of this video you will understand not only what the arithmetic derivative is, but also appreciate its exceedingly interesting emergent properties. The equation of interest is 2n double prime minus n prime minus 4 is 0. But what do I mean by prime? What is n and what values can it take? To answer that, I must first define what it means for a number to be prime, and we can build from there. But before all that, there are some things you need to know. So the following sets, as seen on the video, are called the natural numbers and the integers. Now the natural numbers, for my purposes, begin with 1, and then just count upwards, so 1, 2, 3, etc. The integers are similar to this, except they include 0, and the negative numbers that are counterpart to the natural numbers. It will also be helpful if you know what a divisor is, or a factor, those are the same thing. Finally, it will be useful to know how to take the intersection of two sets, and to know what the empty set is. Now we should have everything we need, so on to the rest of the video. What is a prime number? Well, they're a certain kind of natural number. A natural number n is prime if it has precisely two divisors, 1 and n itself. But what is a divisor? We say that a number k is a divisor of n if we get a whole number when we divide, hence the name, n by k. As a result, we have that 1 is a divisor of any number, since n divided by 1 is always n. With this definition, we may now write down the prime numbers, and they go like this: 2, 3, 5, 7, and so on. We note that 1 isn't a prime number because it only has one divisor, which is 1. Now you won't necessarily see this notation everywhere, but I will notate the collection of all such prime numbers using this mathsy looking capital P. An important property of these numbers is that every natural number can be expressed as a unique product of prime numbers. So essentially, primes are the primitive building blocks of the natural numbers, hence the name. Now we know what a prime number is, we can define what n prime is, namely, the arithmetic derivative. So for any natural number n prime is the arithmetic derivative of n, which is defined as follows. So 1 prime is equal to 0 prime, which is equal to 0. N prime is 1 if n is a prime number. And finally, n prime is a times b all prime, which is equal to a prime b plus ab prime. The last of these is the step which borrows from the derivative you may be familiar with in calculus, namely the product rule. This states that for any two functions, f of x and g of x, that we can take derivatives of, the derivative of the product of these functions follows the following rule. The derivative of f of x times g of x is f prime of x, g of x, plus f of x, g prime of x. As you can see, this is exactly the same as our rule, except our f of x and g of x are divisors of our original number n, as opposed to functions. And that's all the calculus required for this video. Using our definition, we can now list the values of the arithmetic derivative, and I will explain two of the more complicated examples below just for practice. For n being the natural numbers, we have n prime is 0, 1, 1, 4, 1, and so on, as you can see on the screen. Now moving on to some specific examples, we have that 4 prime is 4, since we can write 4 as 2 times 2. Hence, 4 prime is 2 times 2 all prime, and that's equal to, by our product rule, 2 prime times 2 plus 2 times 2 prime. Now since 2 is prime, 2 prime is just 1, so our derivative ends up being 2 plus 2, which is of course 4. Another example is 6 prime equals 5. We can write 6 as 2 times 3, and hence 6 prime is 2 times 3 all prime, which becomes 2 prime times 3 plus 2 times 3 prime, which, because 2 and 3 are both prime, is just 2 plus 3, which is of course 5. Now it can be proven, although it won't be in this video, that this arithmetic derivative is well defined for any natural number n. What that means is that for any two valid factorizations of n, our product rule will return the same number when applied to both factorizations. As a result, we can apply the arithmetic derivative repeatedly to a single input. And this is what n double prime means. We apply the derivative once, and then find the derivative of that result. We now have all the components required to form the equation I want to talk about, but first I'd like to explain its difficult sounding name and where that comes from. Our equation is called the second order prime power equation, but just repeating that raises more questions than it answers. Specifically, is there a first order prime power equation? Well, yes, and we actually already saw it. It will make sense to define the more general nth order prime power equation and then recover the first and second degree cases. Now, the nth order prime power equation is an equation in our arithmetic derivative such that the nth prime powers are solutions. So, the first order case is an equation where the primes are solutions, and our second order case is an equation where the primes squared are solutions. From this, it's fairly trivial to see that the first order prime power equation is simply n prime equals 1, since this is the case only when n is prime. But what about our equation, which concerns the square primes? Now I claim that the equation 2n double prime minus n prime minus 4 equals 0 has at least solutions of the form n equals p squared, where p is some prime. And I will prove this now. Using the definition I showed before, we can find the arithmetic derivative of p squared with relative ease. We have n prime is equal to p times p, all prime, which is p prime times p plus p times p prime, which is equal to 2p. Furthermore, we can keep going, obtaining n double prime, which is of course 2p, all prime, which ends up being 2 prime p plus 2p prime, which is equal to p plus 2. These values can now be substituted into our equation as follows. This then shows that for any prime, its square must be a solution of my equation. When I first found this, I wanted to see if this completely describes the solutions of the equation like in the first order case. So I booted up Python and wrote some code to solve the equation by just trying every number up to some large values. The results have kept my spare time occupied for the past few years, and are still not, and as I will explain, can never be, completely classified. Here are the solutions less than 100. You have n is 4, 9, 21, 25, and so on, as you can see on the screen. Now the first two are what we would expect. Specifically, 4 is 2 squared and 9 is 3 squared. But 21 isn't a prime number squared. In fact, it's 3 times 7. And neither is 85, which is 5 times 17. In fact, the solutions we actually wanted constitute a seemingly small proportion of the solutions we end up with. And this was very puzzling for me. So, as one does when seeking to explain some sequence of numbers, I began to look for patterns. For terms which are suitably small, solutions appear to be of three kinds. The first are the solutions we actually want, n equals p squared. Now the second appear to be n equals 3 times some prime number, but not all primes. For instance, 2 times 3, which is 6, is not a solution to our equation. The final category is that n is neither of the initial two, but still only has 2 prime factors. It turns out, however, that these three cases are, first of all, describable mathematically, second of all, incredibly interesting, and lastly, however irritating this may be, an incomplete description of all of our solutions. To describe the second type of solution, we need to take a look at modular arithmetic, specifically modular arithmetic mod 4. Now what that means is rather than just having the natural numbers going on to infinity, we loop round, starting instead at 0, and going 0, 1, 2, 3, and then wrapping round to 0. And what this effectively tracks is the remainder when you divide a number by 4. For instance, any number which is a multiple of 4 divided by 4 has no remainder, so we say it's equivalent to 0 mod 4. When a number has remainder 1 with respect to 4, that number is equivalent to 1 mod 4, and so on for the other remainders. This effectively splits the infinite sequence of natural numbers into 4 cases, and handily for our purposes, splits the odd numbers into 2 cases. N is 1 mod 4, or n is 3 mod 4. As a result of this, since most primes happen to be odd, this also splits the primes into 2 cases, 1 and 3. And this will be very useful. As such, we can write any odd prime in the form 4k plus 1, or in the form 4k plus 3, where k is just some natural number, or 0 in the case of the prime 3. Now remember this, because this will be very, very useful. Using Python, I analysed these solutions and noticed a pattern. It seemed that the primes that appeared in these solutions, at least, were always of the form 4k plus 3, so 3 mod 4. Now let's just assume this pattern holds, which is generally a bad practice, but it ends up working here, and let's try and figure out what the derivative is under these circumstances. So we now write n is 3 times 4k plus 3 for some natural number k, such that 4k plus 3 is prime, for which we can compute the derivative easily. We get n prime is 3 times 4k plus 3 all prime, which ends up being 3 prime times 4k plus 3 times 4k plus 3 prime. Both of the things we're taking the derivative of here are prime, so they just turn into 1s. So that ends up being 4k plus 3, which is 4k plus 6. It'll be helpful to factorise this so we can compute the next derivative. So we take the factor of 2 out, we get 2 times 2k plus 3. Now we appear to be stuck, because how do we find the derivative of 2k plus 3? And here's the trick. We just say it has to be prime. I know that seems like cheating, but if you see, it actually ends up working out, so just bear with me here. We can now compute the second derivative, n double prime, and that's 2 times 2k plus 3 all prime, which ends up being 2 prime times 2k plus 3 plus 2 times 2k plus 3 prime. Since 2 is prime, and since we're saying that 2k plus 3 must also be prime, this ends up becoming 2k plus 5. Here now comes the magic. Substituting these values into the equation, we find they cancel just as nicely as in our original case, for n equals p squared. Hence we have just shown that n equals 3 times 4k plus 3, where k is some natural number, is a solution of our equation whenever both 4k plus 3 and 2k plus 3 are prime. These are prime numbers separated by precisely 2k, and so, incredibly and unforeseeably, these solutions correspond to some of the Goldbach primes, which are the subject of the Goldbach conjecture. For those of you who don't know, the Goldbach conjecture is an unproven statement in mathematics stating that there exist infinitely many pairs of primes separated by any even number. These we call the Goldbach pairs, at least in this video. Its primitive case is the twin prime conjecture, which states that there are infinitely many primes separated by 2, which is also unsolved. Amazingly, and completely by accident, we've stumbled upon $2 million questions, which is cool and fun and nice, but it pales in comparison to the next case, which is similar but much more profound. For my final proven class of solutions, the derivation is a little more involved. Let us now consider n as a product of two different odd primes, p and q. We can compute n prime easily, which is just p plus q, but we then appear to be stuck. Note, however, that because we said p and q are odd, their sum must be even. Let's say p plus q is 2r for some natural number r. Using this, we can now compute the second derivative, which ends up being r plus 2r prime. Now this still isn't great because we have a loose r prime in our equation, but maybe substitution will tell us more about r. After rearranging, we get that r prime must equal 1, and this means that r must be prime. Now, if we let p and q be a Goldbach pair, so q is p plus 2k for some k in the natural numbers, we must have that r is p plus k, and this gives that k must be even, since an odd number plus an odd number is even, and our primes, our large primes, are odd. Now reusing the letter k, we can write p, q and r as follows. P is some odd prime, r is p plus 2k, and q is p plus 4k. Now note, if we set p equals 3, then the resulting equations are exactly the previous case we explored. Otherwise, a trend emerges. For p not equal to 3, it seems that our k is always divisible by 3. Though a counterexample might exist, I haven't found one. Relating this back to our equation, we get the following solutions. N is p times p plus 12k, where p plus 6k, and p plus 12k are all prime. This result is fascinating to me, as when we set k equals 0, it collapses back to the first case, n is p squared. Yet it reveals so many more solutions, each corresponding to a prime triplet. I call the set of all such triplets the triplex primes, and from our equation there seem to be infinitely many. We can, however, make a larger conjecture. There are an infinite number of prime n tuplets, that's a tuplet containing n primes, with common distance n factorial k. Here, the factorial function is simply n times n minus 1 times n minus 2 all the way down to 2 and then 1. This lines up with the Goldbach conjecture because 2 factorial is 2. It's all well and good me just stating this, so here are some examples. Feel free to pause and check these if you have the time or really want to. Returning now to our equation, we might expect that we have described all of the solutions, but this is not the case. Using my Python program, we have successfully classified solutions up to around 1000, with the unclassified solutions less than 5000 beginning 1155, 1995, and so on, as you can see on the screen. Of these, each seems to have 4 factors. Examining these using modular arithmetic, I make the following conjecture. For a solution n is PQRS, for primes PQRS, where P is 4a plus 1 for some natural number a, Q is 4b plus m for some natural number b, R is 4c plus m for some natural number c, and S is 4d plus 3, we have 2 cases in M. Either m is 1 and the expression a on the screen, which I'm not even going to try and say, is prime, or we have that m is 3 and the expression b on the screen, which again I'm not even going to bother with, is prime. Now these seem to be absolutely disgusting, but they do seem to work, as I'm going to show. So the first solution of this form is n equals 1155, and this can be written as 5 times 3 times 7 times 11. Now I know I've put the primes in a strange order, but that's so they line up nicer with how I've described the conjecture. We have that 5 is 1 mod 4, and the rest of the primes, 3, 7 and 11, are all 3 mod 4. And so this is the case m equals 3, where our numbers a, b, c and d are 1, 0, 1 and 2 respectively. Note that b being 0 is actually quite nice here, because we can cancel any term with b in it. We then substitute these values into the expression b and figure out if that number itself is prime. And it is. It ends up becoming 443, which is prime as required. Now there is another check we have to do here. Our expression b should be equal to precisely half of n prime. But why is this the case? It's complicated, but I'm going to try and explain now. The substitution we need is called a prime reduction substitution, and rather than being on n, it is on n prime. This is the case and is useful because it reduces, hence the name, the order of the equation from a second order equation to a first order equation. Generally speaking, the substitution is to let n prime equal p times k, where p is some prime and k is some natural number. In our case, however, we're just going to use p equals 2. Hence, we get n double prime is k plus 2k prime. Now substituting this and rearranging a bit, we end up with k prime is equal to 1. Now we've seen this before, it just means that k has to be prime. So what we've just shown is that n is a solution to our equation whenever n prime is 2k, where k is some prime number. This ends up being useful because it limits us to a single case mod 4 whenever n is a solution. On the screen is an argument for the following. If n is a solution, then n prime must be 2 mod 4. Using this, and what I call the technique of modulo derivatives, which I will explain in a second, we can use it to rule out cases in n with any number of prime divisors. For this method, we're going to need a little bit of new notation, and just bear with me here because it's slight abusive notation from what you may be familiar with, but it does work in producing functional and useful results. So we're going to let P1 be a general prime of the form 4k plus 1. So that means P1 isn't a specific prime number, it just represents any prime of that form. Similarly, we're going to let P3 be a general prime of the form 4k plus 3. Just as a warning, the next slide is a bit of a mess symbolically, but I'll try and walk you through it as best as I can. So there are 2 tables here. I'll first explain the simple one in the top right hand corner and then move on to the more complicated one, which is our actual working in the middle. The one in the top right is a multiplication table mod 4, and the easiest way to think about this is just that it's an extension of how we think about even and odd numbers when we multiply those. So think that when you multiply an odd number by an even number, you get an even number. When you multiply an odd number by an odd number, you get an odd number again. And when you multiply an even number by another even number, you get an even number. That's exactly the same as this, except this is case as mod 4, as opposed to the even odd case, which is just mod 2. Now for the sake of brevity, I'm only going to cover one of the rows in the second table, because they all work out fairly similarly. The first row considers all numbers n of the form p1 times p3 cubed. And what that means is n with 4 prime factors, one of which is of the form 4k plus 1, and 3 of which are of the form 4k plus 3. Note here that p3 cubed is not the same prime of the form 4k plus 3 cubed, it's any 3 primes of the form 4k plus 3. Now, using the product rule a couple of times, we can differentiate this n to get p3 cubed plus 3p1 p3 squared. We can evaluate this mod 4 as follows. We can work out p3 cubed as that's just a number which is 3 mod 4 cubed. So if we see 3 times 3 is 1 mod 4, and then 1 times 3 to make 3 cubed is 3 mod 4. That's where you get the first 3 from in the sum for n prime mod 4. Then the second one is 3 times whatever p1 p3 squared is. Now, we already saw from before a number which is 3 mod 4 squared is 1 mod 4. We now times this by p1, which then again just produces another number which is 1 mod 4, and this is then multiplied by 3. So that's where the second 3 comes from in the n prime mod 4 column. Adding 3 and 3 gives 6, which is 2 mod 4, which is exactly the case we want. So this can be a possible solution. So why do we care about this? Why is this in any way useful? It effectively allows us to skip a lot of horrible algebra. More specifically, for 4 prime factors, each expression we must compute is the sum of 4 products of 3 different prime numbers, all in the form 4k plus 1 or 4k plus 3. For each of these prime numbers, we can't just use the letter k, we have to have a different letter for each prime, and so our resultant expression is multivariate. In fact, it's in 4 different variables. Now, I don't know about you, but I certainly do not want to be sat expanding brackets for that length of time. So I must admit, I did cheat a bit to get the expressions. I used Symbolab, which is an online resource which allows you to expand algebraic expressions and simplify them, to get the expressions that I showed. So are we now done classifying solutions? No. The first that doesn't fit any of the patterns I have laid out is the number 345,345, which is a very satisfying number, which has 6 prime factors. We can again use the method of modulo derivatives to find that there are 2 cases here. The first being when you have 4 factors of the form 4k plus 1 and 2 of the form 4k plus 3, and the second being when you have 2 of the case 4k plus 1 and 4 of the case 4k plus 3. Now, the expressions that would result from this analysis would be in 6 variables, which is too many. I'm not going to include them. I tried and they were wrong, so I'm not going to put them in the video. Instead, I think our time would be better served finishing this video by giving you a nice introduction to another part of natural calculus, which also links to this equation, called the arithmetic integral. Thinking back to our prime reduction substitution, we found that n is a solution of our equation if n prime is 2p for some prime p. And this implies 2 statements, each of which I will go through separately. The first of which is obtained by first dividing by 2, and then taking the derivative of both sides, noting that the derivative of a prime is always 1. Alternatively, we can write n belongs to the union for p belonging to the prime numbers of the arithmetic integral of 2p with respect to the natural numbers. Now, what on earth did I just say? I will explain in a second. First, I will explain the first statement, which is a lot easier and actually quite nice. The studious amongst you will notice I haven't told you how to differentiate a fraction. But don't worry, the fact that we borrowed a product rule from calculus means it ends up very similar to how we differentiate a quotient in regular calculus. Namely, we use the quotient rule. A proof of this is seen on the screen. We can now apply this quotient rule to the expression we have, and actually recover our original equation. So we have n prime divided by 2, all prime, becomes 2 times n double prime minus 2 prime n prime, remember 2 prime is just 1 because 2 is a prime number, all divided by 2 squared, which happens to be 4. We then multiply both sides by 4 to get 2n double prime minus n prime is equal to 4, and move the 4 across, and we have our original equation. Isn't that nice? To finish, as I said before, we will be taking a brief look at the arithmetic integral. So what is that? Similarly to calculus, the arithmetic integral is effectively an inverse of the arithmetic derivative, and it's defined as follows. I of n, or the arithmetic integral of n with respect to the natural numbers, is the set of all numbers k such that k prime, so the arithmetic derivative of k, is equal to n, which is the number we used in the argument for the integral. This is still a bit nebulous, so I'm going to do some examples just to illustrate what I mean. Consider that I of 1 is all of the prime numbers, since every prime number maps to 1 under arithmetic differentiation. We can also show that I of 2 and I of 3 is the empty set, so that is the set containing no numbers, and this corresponds to the fact that no numbers produce 2 or 3 when you take their derivative. We have I of 5 is the set containing 6, I of 6 is the set containing 9, and so on. I'm not going to list them all because they're all sort of random. Note that for the values 6 and 10, which are each twice a prime number, 6 being 2 times 3 and 10 being 2 times 5, we have that 9 works in our equation, as does 21 and 25. What this second implication effectively means is that all of our solutions have some associated prime number, for which, when you find their derivative, it's equal to twice that prime number. This, rather than splitting into infinite solution classes, splits our solutions into finite chunks, which is actually both better and worse for reasons I will discuss now. It's better because we avoid all the horrible algebra involved in the old method, but it's also worse because we don't actually know the highest number that an arithmetic integral can take. It appears to be the case that for our integrals of 2p, the highest number that integral can take is p squared, although this isn't proven. And that's it. Thank you very much for watching this video if you've reached this far. This is the first time I've ever tried doing something like this. I don't know how it's going to turn out. I don't know how understandable I'm going to be, but I hope you've enjoyed this ride through my field of natural calculus. I'd like to thank Grant Sanderson at 3Blue1 Brown for both hosting the Summer of Maths Exhibition 23, but also inspiring me, not just to make this video, but in all of the content that he makes, because he's a fantastic YouTuber, and I would really suggest if you are interested in maths that you go check him out. I would also be remiss if I didn't mention the video that inspired this. There's a YouTuber called Flammable Maths, who does videos on various mathematical topics, and he is very, very good. He did a video on the arithmetic derivative a few years back, which I'm going to link in the description, which really inspired me to look into this to begin with. So it's really thanks to him that this video got made in the first place. I hope you have a wonderful day, like, subscribe and whatnot, and I'll see you in the next one.